Hello. In this talk, we are going to talk about the top 10 insecure by default IAM configurations in AWS and GCP. I'm Gergely Dányi, the CTO at P0 Security, where we are building a tool for universal access governance for the cloud. Much of the content that you see in this talk comes from our experience building the product. Why is this even a topic? If you look at the history of security breaches in the cloud, there is always an identity involved. The identity has IAM permissions which define the authorization of this identity. And these permissions enable the malicious actor to go about their business. The identity can either be a human or a service identity. And their permissions really define the blast radius of the attack, define what this threat actor is able to accomplish. Let's look at a couple of motivating examples, one for each type of identity. The first one is the Capital One breach from 2019. Here, there was a backend service that was accessed by an external threat actor. And although the details are not available, we can speculate that likely this backend service had permissions to access data that was not really needed for the task that it was accomplishing. So the attacker was able to ultimately download consumer credit applications of millions of customers. The other example is the LastPass breach of last year. Here, there was a senior SRE engineer, a privileged human identity, who had permissions to access vaults of customers' passwords, encrypted vaults of customers' passwords in S3. Here, the attacker, using a sophisticated, very targeted method to be able to impersonate this SRE, was able to download these vault backups, which is dangerous because then they can brute force these vaults to try to crack the master passwords. Before we jump into the top 10 exactly, let's see how we define insecure and how we define by default. Insecure in the light of the previous examples means that there is some risky permission. For example, reading data from S3 from a bucket that contains sensitive information, which highlights that the definition of insecure differs from environment to environment. It depends what you store. It depends on what you store on in that S3 bucket. There's also an element of unexpectedness. Sometimes you may think that the way the permissions are defined is secure and it contains only permissions that are needed, and on the surface it looks as if everything's okay, but those permissions that you've granted actually allow some kind of escalation path or grant abilities that you were not expecting. By default, I hope is rather obvious. It means that if you just click through the wizard, if you don't change any of the defaults in the form, then you will end up with this insecure configuration. And with that, let's start with number 10, pre-signed or signed URLs. Why this made it onto this list? Because signed URLs allow circumvention of IAM by default. In AWS, they are called pre-signed URLs. In GCP, they are called signed URLs, but they are the same functionality. It means that even if you have a private bucket that you have disabled public access for, the owner of the bucket or the owner of the objects in the bucket is able to generate signed URLs that inherit the permissions of the creator. And then these signed URLs can freely be shared with anyone. And whoever possesses the signed URLs can access the objects that the signed URL points to. Let's look at the use case or the reason for existence of this feature. Why does this feature even exist? There's a very valid reason. If you develop an application where there are many users that you do not want to authenticate, and these users upload their data to your service, you process their data, you store the processed data in S3 or Google Cloud Storage, and then you generate a signed URL or pre-signed URL that you return to the user. Now the user is able to, without crossing your service, go directly to S3 or GCS and download that data or upload whatever you generated the pre-signed URL for. A very valid use case. However, keep in mind, not all applications are architected this way. And even the ones that are not, even the buckets that are not part of such an application have pre-signed URLs enabled. An exploit example is this HackerOne report, where somebody was able to access files using path traversal using the pre-signed URLs. What can you do against this? You can completely disable pre-signed URLs on S3 by setting an IAM condition on the S3 :auth type IAM condition. If you specify this as REST query string, it means that no pre-signed URL requests will ever go through, as long as the effect you specify is a deny effect. In Google Cloud, you cannot disable signed URLs completely. You can control the IAM service account's signed blob permission, which is needed to generate these signed URLs. You also must control service account keys, because with service account keys, users are able to manually generate signed URLs. Number 9, user OAuth. This applies to GCP only. In Google Cloud, well, Google Cloud is one of the services of Google Workspace, just like Google Drive or Google Meet or Gmail. And just like those services, Google Cloud can also be accessed by a third party via OAuth. How does this look? Imagine there's a third-party application, in this case, the OAuth 2 Playground, and it requests some scopes from any of your GCP users. In this case, I requested the Google BigQuery Manage scope. If a user grants this scope to an external application, then the external application that's on the right here is able to execute an actual API request using the scope that they gained. Here, I queried a table in BigQuery using the scope I got from this user. Now, user OAuth is turned on by default. All of your users who have GCP access can authorize a third-party application and thereby grant access to your cloud. What can you do against this? You can go to Google Workspace Admin and turn off Google Cloud Platform for everyone. It doesn't need to be on for everyone, only the people that actually use it. You can also change what applications can access, can be given the OAuth scopes. By default, all applications, but you can also specify a list of trusted apps. Be mindful that the list applies to all of the Google services, not only Cloud Platform. You can also use this new setting called unconfigured third-party apps. Here you have 3 options. You either allow, completely disallow, and the middle option is only allow scopes that are needed for Google sign-in. Number 8, basic cross-account access. This applies to AWS. If you have a setup where multiple AWS accounts in your control need to interact with each other, or there is an external vendor that wants to interact with your AWS account, very likely there will be, this is the setting that you are going to apply. There's another external AWS account or internal that's in your control that needs access to this one. If you set this up in the AWS console, you will trust all of the identities in this other AWS account, which is, of course, a bad idea because you cannot foresee what identities will be created in that other AWS account and who will have the authentication, the credentials to access those identities. The simple mitigation is to trust a specific principal. Instead of the entire account, specify a concrete ARN for the role or user or whatever type of principal you have in the other account. There's an additional safety net, especially when you're working with vendors, that you can require an external ID. This is useful because the vendor will work with many customers, and there is a risk of other customers accessing your account through the AWS account of this vendor. By agreeing on an external ID between the vendor and yourself, and by the vendors always submitting this external ID whenever they interact with your account, you can enforce that, you can mitigate this risk and enforce that other customers won't be able to access your data. Number 7, discretionary access control. Discretionary access control is a type of access control that comes from the world of databases. It means that it is at the discretion of the owner to define further access controls. There are some services in the cloud that work like this. One of them is actually storage, Google Cloud Storage and S3, although it is not turned on by default. Hence, that's not the example I'm taking here. But if you use BigQuery in GCP, BigQuery uses discretionary access control. The example for that is if you look at this table that I created, temp customer to issue, as Bob Sandbox user. Now, if I look at the permissions I have, I am the BigQuery data owner by virtue of creating this table. As the owner, I can do things like further sharing these tables. For example, I could grant access to all users, which means publicly sharing this table. Now, why is this a problem? Why is this insecure by default? It's because once you give someone the ability to create data sets or create tables, they will also be in control of the permissions, which is somewhat unexpected, somewhat not obvious. What can you do against this? You can specify a deny policy. There is no UI for deny policies in GCP, but you can use the CLI where you set, oh, this Bob tryp0com user cannot set the IAM policy, which is the actual ability to define the sharing permissions on the data set. So even though they are the owner, because deny policies always take precedence over allow policies, they will not be able to grant access to all users on the data set. I tried this, and indeed, I was prompted that, oh, you don't have permission to edit. Number 6, unconstrained resource in a managed policy applies to AWS. This is a problem, again, because it will be somewhat unexpected. If your resource contains star, so a wildcard, it means that the permissions that you grant will apply to all resources, including present and future resources. For example, let's take a sensitive action. For example, the IAM pass role permission, which allows you to specify the role that an AWS service acts as. So ultimately, you're able to define the permissions of that AWS service. Which policies contain a wildcard resource for this permission? I wrote a small script to scrape the managed policies data, and these are the ones that I found. AWS Glue console full access. So Glue is a managed ETL solution, and here you can specify any role that begins with AWS Glue service notebook role as a service role. Then there is Amazon Bedrock full access, where the role needs to contain the string Amazon Bedrock. And finally, Amazon SageMaker is a data science tool, and here you can just pass any role that exists to the service. Now, these are all problematic because these roles are actual execution roles. So by creating some sort of resource in the cloud, for example, a notebook, or in case of Amazon Bedrock, an AI agent, that resource will use the permissions that you've given it through the IAM pass role permission. This is how it looks. You say action IAM pass role, and the resource must be something containing the Amazon Bedrock. So this is part of the Amazon Bedrock full access managed policy. This is one of the statements in that policy. Now let's look at a potential escalation path with Amazon Bedrock full access for the sake of example. So what are the prerequisites for this potential escalation? You need the Bedrock full access role. Imagine you've given that to some engineer in your team. And the reason this is a potential escalation, not a real escalation, is because in order to produce this example, I also had to grant the permission to create service linked roles and attached policies to them, which by itself is already an escalation. Maybe I would be able to reuse an existing service linked role, but I used the UI instead of the CLI. In addition, I needed to grant a permission to create and read a vector store to this user. So for the example, I created a user, I've given it these permissions. And finally, this is how it went. I uploaded a small file to S3 called knowledge.txt, which contained statements about customers. Customers ABC, what are they doing in the platform? Customer Banal Baboon is currently evaluating the platform. Now, as the user, as a human identity, I was able to create an AI agent that pointed to this file as a knowledge base. A knowledge base is something that the AI agent is able to process and include in its answers. And then, after I configured the AI agent, I was able to send a prompt, what is the customer Banal Baboon doing currently? And the AI agent, this purple brain icon here, replied with the information from the knowledge base I provided it earlier. Now, to accomplish all of this, it was possible because me as the user, I was able to pass a role to the service, to the Amazon Bedrock service that contained these permissions. Amazon Bedrock AI agent was able to list a bucket that contained the knowledge base. It was able to get the contents of the knowledge txt file. And finally, it was able to create a vector store where it indexed the contents of this file. Now imagine that there's another file, and if I'm able to pass any role that contains the Amazon Bedrock string in it, then I would be able to pass another role that allows the AI agent to read a different file from S3. For example, this sensitive file that is, in this case, actually machine readable. It's a CSV and contains credit card numbers or password hashes. So that's what I did. I created another knowledge base and I created another AI agent, and I pointed this one to this other sensitive file. And even though this is a CSV, the agent was able to recall the phone number or the password hash from this file. So what's the danger? The danger is the wildcard resource on a sensitive action, the sensitive action being IAM pass role. So what you should do is allow list the exact resources that you want to allow, let these actions be part of. So here you have the IAM pass or the sensitive action. Instead of star or star Amazon Bedrock star, you would actually list the resources one by one. Also, on the other side of this equation, all the roles, in case of IAM pass role at least, need to list the concrete S3 buckets that this AI agent is able to interact with. Number 5, unexpected risky permissions in managed policies for service identities. So while the previous one was about wildcards, this is about unexpected permissions. The previous point was about resources. This is about permissions for service identities. Actually, the previous example also fits the bill here because the unexpected risky permission was the IAM pass role permission. Amazon Bedrock full access was a service-linked role. Oh, sorry, not Amazon Bedrock, that's a user role. But the roles that you then can pass with the IAM pass role permission must be AWS service roles, which contain in the AR and the AWS-service-role string. And these do not present a transitive grant risk because you cannot add anybody else to the trust relationship. If you try to do that, all you get is the ability to edit the description, and you cannot specify other principals. But for AWS service roles, the ones that have service-role in the ARN, you can actually grant any other principal to access to this role. In this example, I granted access myself other than the service. Number 4, unexpected risky permissions in managed policies or roles for human identities. So very similar to the previous one, but this is for human identities. Here I went ahead and collected some roles from AWS, some policies from AWS that contain permissions to services that are not obvious from the title of that policy. For example, if you give AWS Lambda full access to someone, they will have S3 access, they will have DynamoDB access. If you grant, for example, Amazon SageMaker full access, those identities will have access to the container registry, to the AWS Cognito service, to S3. Finally, here I have this somewhat different example of the organization account access role. This role is generated by AWS organizations when you create a child account, a child AWS account. Then inside this child account, there will be a new role generated called organization account access role. And this by default has administrator access. In Google Cloud, I went ahead and looked for roles that contain storage or compute permissions, and these are my findings. There is the Cloud Deploy Runner role, which allows you to read any object and create any object on storage. You have the Firebase Viewer, which can read any object from storage. You have the Notebooks Legacy Admin, which has all the actions on compute. So you must be mindful when you grant managed roles or managed policies in AWS to review what are the exact permissions that they contain. You can disable certain risky access with a service control policy in AWS. The example for this we will cover later. But the idea is that once you know what you care about and what you do not want to allow, what actions you do not want to allow, you can disable them. You can also detect policies using a service called AWS config. In this case, you do not need to know the permission, the actions themselves. You can just monitor one policy, one managed or multiple managed policies, and whenever somebody gets that policy assigned, you will get a warning. Unfortunately, this is not an enforced control, it's only a monitoring control. In Google Cloud, you can specify a deny policy on sensitive permissions. We already showed how to do this with the discretionary access control example. If you want to deny a sensitive permission altogether, you can just set the principal set to all. Number 3, default attachment of risky permissions to service identities. So in the previous example, we saw policies, managed policies, and roles that exist out there, and you may configure them as the role or policy for your service or your human user. But in this case, in number 3, what we see is there is some action in your cloud that actually triggers the attachment of permissions to identities behind the scenes by default. This happens in Google Cloud. There are 3 types of service accounts in Google Cloud that get permissions assigned to them automatically. The user-managed service accounts there are only 2 user-managed service accounts, the compute engine and the app engine. These get by default the editor access, so they can do anything in your account. Make sure you fine-tune their role. In this example, I changed the role of compute engine to data proc worker from editor. Then you have the Google managed service accounts. Those are going to be the ones where the icon in the UI is not a little key, but this little hexagon. For example, the cloud build service account, which gets its own role, which has a lot of permissions that you should review. And we also have service agents, which I'm actually not sure whether service agents is a subcategory of Google managed service accounts. They definitely show up as with the hexagon icon, and they will only be visible if you also check the box and include Google provided role grants. Now, it is not recommended to change the permissions of service agents unless the IAM recommender prompts you to do so. So the mitigations are, as I mentioned, edit the defaults. If you see a service account is completely unused, for example, let me go back. If you see the Firebase admin SDK service account is completely unused, chances are that this was created, but then the features that need these service accounts are just never used in your infrastructure. So it's probably safe to remove these unused service accounts altogether. Then you have some organization policies in GCP. So organization policies will enforce policies in your entire organization, and they will improve your security posture. One thing you can do here is disable automatic IAM grants for the default service accounts. This applies to App Engine and Compute. There's another control for disabling the Cloud Build service account. Finally, you can do You can restrict the allowed Google Cloud APIs altogether. So this will indirectly prevent the creation of service agent roles. It's a good idea to explicitly list which are the Google Cloud APIs that people can work with. And there are two others that you can review for yourself. The one that I marked with a green check mark is part of a new secure by default package, which is rolling out in 2024 April. And this means that new GCP accounts will have all of these organization policies turned on by default. And disabling, so the first policy here is one of these. Number 2, long-lived keys enabled by default. In AWS, everybody knows about user access keys. These keys are used for CLI access typically. In Google Cloud, we have service account keys. So it's not meant for human identities, it's meant for a service authentication where you would create a key and embed the key in your application. There's also a lesser known concept of API keys. API keys work only with a few GCP services, mostly related to machine learning, such as Cloud Vision or text-to-speech. And API keys can be generated by users, and whoever has the key behaves very similar to the others. Whoever has the key has access to those services. So the problem with keys is it's very hard to track where they are used from and why they exist. Rotation of these keys is very hard. So the best would be not to create them at all in the first place. Now, be mindful that in AWS, even though they are called user access keys, users can be service identities. In this example, I was setting up an integration with Okta, and Okta actually prompts you to provide a user access key that it can use to authenticate. What can you do instead of AWS access keys? For human access from the CLI, you can grant the Cloud Shell full access managed policy to your users. In this case, they will not interact with the CLI from their local machine. They will log into the web UI, the AWS console, and create a Cloud Shell there. You can also change the authentication scheme to something that supports short-lived credentials. You can use AWS Identity Center or Account Federation. In these cases, your users will continue using the CLI locally with short-lived credentials. Here's an example of configuring Google Workspace as a SAML provider. If you use access keys for service access, you should consult the documentation of the service you're using. If you're using EC2 instances, the recommended way of granting permissions is the instance profile. If you are using Kubernetes, EKS, you can use the IRSA, which stands for IAM roles for service accounts. So you can link a Kubernetes native service account to a role in AWS. If you are using services that might be outside AWS or on-prem, you can use the IAM roles anywhere system, which is a certificate-based mechanism for getting temporary access tokens. Finally, you can use the assume role with web identity action in the trust policy, which is an OIDC access token. This is how, for example, P0 integrates with your AWS account. What can you do in GCP? Well, first thing is that in GCP, even though service accounts are meant for service accounts, very often what we see, companies or development teams will also generate service account keys for local development. Since that's how the production system works, in order to be like the production system in the development environment, there are service account keys generated. Well, in fact, if you just use the application default credentials, it will do the right thing. So an example in code, you just instantiate a storage client without any parameters. It will use the default service account, and the default, if it's running in production in an environment, in a VM, for example, then it will use the identity of that VM. If it's running locally, then it will use your Google login credentials on your machine where you're working. For service access, you can use, as I mentioned, consult the documentation of that service for compute. There's a compute service account that's attached to the machines. If you use, for example, Kubernetes engine or any external service, you can use workload identity federation. In this screenshot, I'm showing how to use workload identity federation with GitHub. If you have a GitHub Actions pipeline that needs to deploy something in your Google Cloud, you can set up an identity federation. You can set up a provider, and you will get assertions from GitHub about which repository is trying to take that action. And you can attach the provider to a service account in GCP, and you can attach permissions to that service account. How can you disable long-lived keys? In AWS, you can use a service control policy on the IAM create access key permission, which is needed to create them. In Google Cloud, you can use an organization policy to achieve the same. This is also going to be part of the new Secure by Default package. You can also set a service account key expiry, because one of the other problems with service account keys and even AWS token user access keys is that they never expire. But be mindful, this expiry applies, like blanket applies to all of your service account keys. You can also automatically disable exposed service account keys, because Google tracks what keys have been exposed, known to be exposed, and will just go in and disable them if they happen to be yours. For API keys, you can create a deny policy on the permission that allows them to be created. And if you want to prevent access to an existing API key, you also need to control the API keys.keys.get permission, which is part of the viewer, the basic role viewer. Number one, default administrative users. If you've ever set up an AWS or a Google Cloud account, you know how this starts. In AWS, you log in with a root user. In Google Cloud, you land as the organization super admin in your cloud account. Now, the root users are problematic because they need to exist. This is how the account is set up. And by default, they're going to be there forever. They're going to have all the permissions to your kingdom, and they are going to be the prized targets for hackers. So what can you do, and how do they come into existence? When we talk about these root users, it's important that we also talk about the authentication of the root users, because that is your first line of defense. So when you create a new AWS account, and in this example, I'm using AWS organizations to create one. Here I specify the email address, and this email address is going to be the root user of my new account. Then I create the account, and the password for this user is actually not known. And so you must go and do this the first thing after you created the account. You go to the sign-in page of the new account, and you must click Forgot Password to retrieve the password. And so what are the things that you can do to mitigate this risk? These are the recommendations by AWS. First, I guess, obvious one is to configure MFA. The password should not be enough. Now, note that MFA in AWS is recoverable. So here in the bottom screenshot, I showed you that AWS asks for email and phone number verification. And if these succeed, then you can recover your second factor. AWS highlights the users, or if the users has MFA or not. That's a good thing. Other recommendations: limit the usage of the root user. Only use it for emergency use cases. There are a few tasks that can only be accomplished with the root user. For example, recovering KMS keys. You must raise a support ticket as the root user. But other than that, for the actual routine daily tasks, use IAM users. Do not create the access keys, period. And finally, monitor the usage of the root user. You can set up CloudTrail logs to do that. Other things you can do. You can limit the root user's access with a service control policy and with AWS Control Tower, and we're going to look at those in a moment. An SCP in AWS looks like this. This is an AWS organizations feature. You must enable AWS organizations, but you can specify a policy which says, oh, the principal called root cannot do anything in AWS. And I tried it, I logged in as root, and I wasn't able to interact with S3. Now, be mindful that service control policies do not affect the management account in AWS organizations. If you want to control permissions of the management account, you can use this feature called the delegated administrator account, where you will appoint one of the child accounts as the admin account. AWS Control Tower is another service that operates inside AWS organizations, and for each of their controls, they will use different services, other AWS services. For this particular control called disallow actions as a root user, they also use service control policies, but they are a bit stricter here. They just deny all actions for the root user. Be mindful if you do something like this, in an emergency use case, you will first have to remove this policy. You can also disallow creation of access keys. This is very useful. You can just say, hey, the root user is not allowed to create an access key. Number one, for Google Cloud, we have not talked about the organization super admins yet. Super admins of GCP are the Google Workspace users that are super admins. So super admins will have the privilege to define who is the organization administrator inside GCP. So by virtue of this, they can actually define indirectly all of the permissions in GCP. What can you do? You can set MFA. In Google Cloud, though, be mindful, there is no recovery. You can generate user reports to check if your super admin has enrolled in MFA. And the other recommendations are similar to AWS. Limit the usage of the super admin and monitor the logs. The other thing you can do is you can disable the password recovery for super users. This is something you can do in Google Cloud in the workspace admin settings. Here's how you do it. Other things you can do in both AWS and GCP. You can split the factors. So somebody has the password and another person has the second factor. You can define a second admin email. So whenever I log in as the admin, that's where I really want to accomplish those super admin tasks, those root tasks. You can use a group email as the root user or the super admin. And this is useful because both AWS and GCP, they will send you notifications about suspicious activity, and then an entire group of people will see that. Of course, don't share the password with the entire group of people. And finally, here is our universal access control product, P0 Security, where you can monitor, define, and enforce some of the policies that we discussed today. And also move to a model where you can grant permissions just in time to users as they need it. Thank you for listening to this talk.